Welcome back, everyone. I am going to show you how to start actually running statistics. So once our data has been cleaned, there are lots of options in R to run statistics. So I guess I have one more data cleaning thing that I wanted to show you before we move on, and that's how to create scales in R and how to create scales and work with them. So first of all, we need to use the relationship data, which I have here. If you need to import it, then you can go back to a previous file. The relationship is right here, so it's a DTA file, so remember the haven and then read DTA. You can bring it in if you don't have it. Let's look at a bit of the relationship just to show you here what we can do. Okay, so look, this even has some labels in there, which is pretty cool. So I want to create a scale from RSAT 1, 2, 3, and 4. Now, we use scales when we try to assess a construct with multiple questions. The most common way of dealing with a scale is just by doing an average. So I'm just going to create a new variable by giving my data set name and then just giving a new name that's not in there. And this does require a bit of math because I'm actually just going to create the average by hand. So I go relationship $RSAT1 plus relationship $RSAT2, so on until we've got all 4 of them. And I put that in parentheses so that I can divide by 4 and have everything divided by 4. So this will do it for each of the rows. So now if I look at, I've got to reload this. Now I've got satisfaction that's the average of these 4 items. So this first person had 4 on all of them, so the average is 4. But this person had 3 on 3 of them and a 4, so that brought his average up to 3.25, and so on. So we've created a scale that's the average of their 4 items. And I know that other programs like Stata have just a row mean function rather than actually like typing out the average, but I found that in R it's more math based, so it's easiest to just type that out. Yeah, so one thing that you need to do whenever you are dealing with a scale is also compute a reliability coefficient. This is kind of like, I describe it, although mathematically it's not exactly like this. It's kind of like a correlation among as many variables in the scale as you have. So it's going to be like a joint correlation between these 4 items if we compute an alpha coefficient. So we just say alpha, and then inside here we say relationship, and then we're going to specify a subset of the columns. So give me square brackets, all rows, comma, create our vector here, RSAT1, RSAT2, RSAT3, and RSAT4. And then you can also specify na.rm equals false, and that means do not remove missing data. Missing data is specified as an NA in R, and RM is remove, so I do not want to remove the missing data. Okay, so let's look at this. Raw alpha is 0.96, standardized alpha, average R, I mean, that's the value that you're going to be probably putting in your manuscript, and there are some other things here that reliability if an item is dropped. So if you drop RSAT 1, then your reliability is 0.94. If you drop RSAT 4, your reliability is 0.96. That's really useful for when you want to know if maybe one of these items doesn't correlate well or load well with the other items. That's a good test that can show you about it. All right, so once we have our data, I'm going to go to basic statistics. So for those of you that are following along using our markdown files, I'm now moving from 1 to 3. I'm going to bring this data set in. Again, I could just run it there, but I don't want to overwrite any of the stuff that I've done with that, so I'm just going to run it myself, and now I have ER visits. But I'm going to type it out myself, and I recommend you do the same thing just so you learn it. So yeah, as I've said before you run any statistics, it's good to run some basic frequencies and descriptive statistics. So I'll show you, let's run some descriptive statistics for the miles per gallon, the horsepower, and the cylinder for empty cars. So we've got like a mean of 20, we've got an average horsepower of 147, and an average of 6-cylinder engines. If I wanted to do this same thing, except get the frequencies, I would go Summary Tools, Frequency, and then I'll just copy and paste that same thing since I want the same subset. And it gives me, I've got 7 cars that have 6-cylinder engines, 14 cars that have 8-cylinder engines. Those are my horsepower values, so I've got 3 that have 110 horsepower and a whole bunch that have lower than that. And then we've got some miles per gallon here. Okay, so now that we know a little bit more about our data, let's run a t-test on it. Although I won't actually be using the data for this example that I just ran, but get to know your data before you run it. So the way you run a t-test is t.test, and you put in your main variable that you want, and then a tilde, and then your grouping variable. So for those of you that don't know what a t-test is, I assume that there's that everybody knows what these statistics are that I'm going to run, but I'll explain a little bit more about it. This is a paired samples t-test. Nope, this is an independent samples t-test. And I want to find out if I differ on my GPA based on whether I am male or female. So when I run it, then I guess this is a 2-sample t-test. Welch 2-sample t-test. Look here, my confidence interval does contain 0, and my p-value is greater than 0.05. So we have to do some hypothesis testing, and if your p-value is greater than 0.05, it means we fail to reject the null hypothesis, but basically it means that these two are not significantly different from each other. So that mean and that mean, the differences we see could just be due to chance. So that's an independent 2-group t-test. If we want to do a paired samples t-test, that looks at whether we've changed. So within one person, have they changed? So maybe like a pre-test and a post-test. I'm going to give an example of ER visits in the year 2000 and ER visits in the year 2001. And then paired equals true. So I want to know, did my mean of ER visits, how many people visited the ER in 2000, is that different from 2001? Right off the bat, I've got a p-value that's less than 0.05. My confidence interval does not contain 0, which means that I would assume, I would argue based on this, that my means are different. There it tells you your alternative hypothesis, there's your mean differences, so then you could use the summary statistics to figure out like the exact mean. And I can figure out how to do that by saying aggregate, and I'm going to grab my data set, so grab ER visits. Sorry, I don't need that. It's actually simpler than that. It's just, you say mean of ER visits, sorry, I was spacing out for a little bit, of Y 2000, there it is, and mean of ER visits Y 2001. Oops, sorry. So I have a statistical test that tells me that 372.96 and 380.86, the differences we see there are not likely to be due to chance. They're likely to be due to inherent things within the populations. So that and that are statistically different from each other. Oh, sorry about that. Okay, so that's a mean difference. You could do, other ways that you can do a t-test are with a t-test against a value. So this is a one sample t-test against a value. You go ER visits. We'll see, is the mean of ER visits from the year 2001 different from 400? The answer is no. And we saw that it was 380. So, okay. We could say t-test of ER visits year 2002 from the value of the mean of ER visits year 2001. So this tells me, am I significantly different from that? That line and that line are similar, just in a different way, but I'm just showing you that you can compare against a specific value. And I'll give an ANOVA here, and then I'll move on to regression and correlation in another video. So within ANOVA, it's a two-step process. First, you have to what's called specify the model that you want, and then you have to look at the model that you want. So I'll show you how to do this in 2 lines. I like to just call it M1. This is a name that you come up with, and you say AOV for analysis of variance, and you give your main dependent variable tilde your main independent variable plus any controls that you have, and then you tell it what your data set is. So again, an analysis of variance is kind of like a t-test, except it allows you to control for other influences. So we want to know, do my miles per gallon differ based on how many cylinders I have after I look at how much displacement those cylinders have to go through with the data empty cars. Okay, you run it, you don't see anything. I mean, it showed up there, which is great. But now I say ANOVA M1, run that, and now I see I've got some significant codes down there. Do I have significant differences on MPG based on my cylinder? Yes, I do. And the great thing about an ANOVA is that a t-test requires 2 groups. A cylinder, an ANOVA, can do multiple groups. So across all of our cylinders as a categorical variable, do I have significant differences? And the answer is yes, I do. There's even some significant, well, there's almost some significant differences on displacement, but the important thing is that there are differences even after controlling for how much displacement there is. So that's the t-test in ANOVA. Those are the mean differences kind of tests that you can run and how to do them in R. The next video will do more of the correlation, association, and regression type statistical methods. Very basic, but important.